Okay, so we're sort of rewinding now to just after we'd solved for block 2. I've carried over sort of the two things we found useful the first time we solved the block 1 stuff, just because they'll be sort of handy to have. But we're rewinding to where we've just done the analysis for block 2, but we haven't done the analysis for block 1. What I'm going to do instead of doing the block 1 analysis is I'm going to look at the whole system. Okay, so instead of this diagram, what we actually have here is a block of mass m1 plus m2. Can we do this? Is this really legal, Dr. Smith? Yes, it is. Here's why. Both of these blocks are accelerating at the same rate, right? So the acceleration, the acceleration of this system, of this pair of blocks, is just a. Okay, to the right, and this force is acting on the system. Okay, so there's this force. Well, if they're both accelerating at the same rate, if this pair of blocks with a total mass m1 plus m2 is accelerating at this rate, this force, if this is the only force acting on them vertically or horizontally, then that must be what's causing the acceleration. Let's take a look. Does this actually work? Are you serious, Smith? Can you actually do this? Well, let's watch and find out. So, vertically, we have m1g. Well, actually, I'm going to do total mass of the thing is m1 plus m2 times g. What's this force here? I'm going to call this just n for normal force. This is a force, now in the real world, this is a force acting on the ground here. Or the ground acting on m1 pushing up. But it's the only outside vertical force acting on the system. So besides gravity. So there you go. That's what it's got to be. And there we go. So let's see. That's all the forces we have acting on the system. The friction is all in here, and it's static friction. Well, the fact that it's static doesn't matter though. The friction is all in here. It's happening between m1 and m2. So that doesn't count. All we're talking about is things from the m1, m2 system that are acting on the outside world. It's as though we took and drew a dotted line around our system, or around this m1 plus m2, and said, hey, what's coming in from outside to affect this? What are the outside forces affecting this? That's gravity and the normal force in the ground, and this F. And what's the acceleration of the whole system? Just A. So this is useful. Anytime you have a system accelerating, a pair of objects accelerating at the same rate, you can lump them together. If they're tied together, you can lump them together, absolutely, if they're accelerating at the same rate. So let's see if we can do a free body diagram for this. So FBD for the whole thing, the whole kit and caboodle. All right, so there's our normal force, there's our applied force F, and there's m1 plus m2 times g. Well, if we do a force balance in the x direction, then that's F. That's all we got acting in the x direction. That's the only external force coming in and acting in the x direction. Now you might be saying, hold on, Smith, what's going on here? Because we had like friction force, acting on this thing, and friction force acting on this thing. Well, yeah, but that's a Newton's third law reaction pair. So there's a friction force acting this way on block 2, but the same forces, equal and opposite reaction, was acting this way on block 1. So yeah, I could add those in. I could, for example, let me just I'm going to do this in blue, and I could add in FF between 1 and 2 and FF between 1 and 2, and I could say then I would have to put that 1 in there and 1 in there, and I would say plus FF between 1 and 2 minus FF between 1 and 2, and they cancel out because they're both acting on our system of m1 plus m2. So I can the only external force acting on this is F. So literally that's my entire set of outside forces acting on acting on m1 plus m2 in the x direction. So that's got to equal the mass of the total thing, which is m1 plus m2, right, times A. Well, hell, that was easy. wait a minute, A, what was A? Oh my god, A was mu SG. So F equals M1 plus M2 times coefficient of static friction times G. We found this from our analysis of block 2. And this here just came out of looking at the whole system. Force equals M1 plus M2 times mu SG. Done. That's the same answer we got when we looked at block 1 separately. Okay, so this way, I'm going to scroll up just to verify for you, and I'm going to explain why we can do this different ways. So it's right here, same answer. This is what we got when we did the block 1 separately. So we did the block 2 first, and then we did the block 1 separately, and we got this answer. What I'm saying is if we hadn't done any of this and just got the block 2 answer and do this, we get the same answer. Now, why does this work? Let me draw an analogy for you that sort of might sort of explain it a little bit. So let me use, I don't know. I've gotten all kinds of critical comments about my opinion of various colors, but I'm going to use this sort of forest green type thing. So go back to like algebra, I don't know, whenever you were solving systems of 2 equations. I don't know if that was algebra 1 or algebra 2, but say where you had like, x plus 3y equals 20 or something, I don't know. And then you had 2x, minus 6y equals 42. I don't know. I'm just making stuff up. Now, so this was your system of 2 equations with 2 unknowns, and you know you can solve this. But do you remember how you could take this thing and, I'm going to switch colors here, add one equation to another and get a third equation? So then you go 3x minus 3y equals 62. Okay, great, whatever. So you can take these two, add them up, and get a third equation. But then if you remember in linear algebra, or when you're doing algebra 1, algebra 2 stuff, this didn't really get you anything extra. I mean, basically adding these two up didn't give you extra information. It wasn't like you really created a third equation for the purposes of like needing enough to solve the problem, because what you had really was, in some way, these are redundant. But what you could do was, if you wanted to solve the equation, you could take this one and solve the equation, or you could take this one and solve the equation, or solve for x and y, solve the system of equations. You could solve it with the first two, you could solve it with the sum plus this one, or you could solve it with the sum plus this one. So any of these purple arcs represents a pair of equations that you could use to solve for x and y. But basically having 2 was enough to determine it. And so it's kind of the same thing here where we're doing the system of equations. Or I'm sorry, we're doing these systems of multiple bodies. Here, up top, we solved for block 2, so we sort of got all the information. We squeezed all the information we could get out of block 2, and then we came down here. We did it for block 1, and doing the analysis for block 1 and then for block 2 gave us all the information we needed to find the force. Okay, or we also found that we could analyze block 1 and block 2 together as one system, and that plus our result from block 2. Because we still had this from block 2. Remember, that was what came in useful. So when we took our result from block 2 and our result from analyzing both of them together, then we could solve for f. So it's as though this is block 2 here, this is block 1, and then this is like the whole system analysis. So the first way we did it was like this with block 1 and block 2. The second way we did it was with block 2 and the whole system. We could also have taken like just a block 1 analysis. So I'd just done block 1, solved for block 1 without block 2, and then done the whole thing and put them together. Hold on a second. Hello. All right, that was Catherine Sheridan just coming in, dropping off her lab. So, right, so we could have actually just done the block 1 analysis and then also done the block 1 plus block 2 analysis and gotten here without ever doing the block 2 alone analysis. You basically just have to do 2 different things. If you've got a system of 2 masses, you're going to have to do 2 free body diagrams, 2 sets of equations generally. you know, and then you can sort of try to pick out which one you think will, or which pair you think, I'm sorry, I shouldn't scroll down like that. You can try to sort of pick out which pair you think will give you the easiest time, but you're still going to have to do two, one way or the other. So, there we go, and I hope that was helpful.